think we're pleased to welcome Professor Ernie Rutter from the University of Manchester. Ernie has a wide range of research interests, including high temperature flow of rocks, partially molten rocks, experimental rock mechanics, petrophysics, hydrofractal propagation, gas reservoir modeling, thermal stresses, just to name some of them. He's also, I think, a supervisor of 45 PhD students over the years. And he's an associate editor of the Journal of Geophysics and a recipient of several prestigious awards. And his talk tonight is Geodynamics of southern Spain and comparable areas of the Western Mediterranean. So it's with pleasure I hand over to you, Ernie, for your lecture.
Thank you, Richard. Can you hear me?
We can, yes.
Very good. Right. So, and you can see the first slide occupying most of the screen, I hope. And you
yes.
can see my laser pointer wandering around as well. Okay.
Yep.
Very good. So the idea here is to talk to you about the particular kind of geodynamic situation which exists through the Upper Miocene and towards the present, particularly in southern Spain, but also in similar areas in the Western Mediterranean. Start with the first slide then. Nothing happened. No, nothing happened. What's it doing now? Oh, I have to press that. Yeah. Okay. Oh dear me, that's not southern Spain or the Western Mediterranean, is it? That's the Western United States. There's an interesting point to be made here, because we're looking at the basin and range terrain of the Western United States. It's a part of the North American crust which has been stretched. It's been stretched and thinned. And when you look at this area in here, you can see these vertical bands. These are topographic ridges, and in between them there are sedimentary basins, which have been produced as a result of the stretching. So a slightly more oblique view, you can see the ridges standing up here in this region, which has been extended. And in a crude sort of way, this is the kind of thing that's going on. You see at the surface, we've got these basement, older crustal ridges, which are separated by topographic lows produced by faulting. These are the places where the erosional debris from these uplifted ranges are being poured in to make sedimentary basins. So this is a basin and range kind of terrain. The crust is being stretched, and because the crust is relatively cool and relatively brittle, it fails by faulting, but the stretching goes all the way through the lithosphere. And once you get into the lower crust of a mantle, the rocks become much more ductile, so they accommodate that stretching by flowing. So it's a bit like a creme brulee with brittle stuff on the top and a much more deformable material underneath. So turning our attention to the Western Mediterranean, it really is quite a complicated place. There is a plethora of mountain ranges here, the Pyrenees, the Alps and so on. And quite a lot of these mountain ranges, which are in these shades of brown and orange, are very, very strongly curved. There's the Alboran-Betic arc, there's the Calabrian arc in southern Italy, the Western Alps, very, very strongly curved, Carpathians too, but also the Hellenides on the southern side of the Aegean Sea. And some of these places have styles of deformation in common. In particular, the southern part of Spain, the Tyrrhenian Basin, Calabrian Arc, and the Aegean and Hellenic Arc. These are all places where the crust and the lithosphere is being stretched, or has recently been very strongly stretched. So the Better Cordilleras and the Aldebaran Basin are being stretched more or less east-west. The Tyrrhenian Sea here has been opened by behind the Calabrian Arc between Sicily and Italy, and the Hellenic Arc has a major region of very, very active stretching going on behind it, which is forming the Aegean Sea basin. And these are all pretty much the same sort of age, from upper Miocene through recent. It's really quite remarkable, and we do need to establish a little bit of chronostratigraphy here. You have here the Cenozoic with the Oligocene passing up into the Miocene and then into the Pliocene. And the focus that we're going to be looking at time-wise is this portion between the base of the Teutonian stage of the Upper Miocene from about 12 million years onwards to the through the Mycenaean stage. So it's the sort of top 7 or 8 million years of the Teutonian. Now, some of the tectonics does continue through to the present time, but as far as southern Spain is concerned, this is very much the focus of the main activities. The peak of the Alpine mountain building, on the other hand, is around 25 million years ago. So we're looking very much at post-orogenic activity, things that happened after the main tectonometamorphic peak of the Alpine mountain building. So turning our attention to southern Spain, there are some fairly obvious key features that one can see. First of all, there's a very, very strongly arcuate range of mountains. The Better Cordilleras here, which are trying to thrust themselves over onto the Iberian foreland, and you have the Rif and the Atlas, Atlas Mountains trying to push themselves over onto North Africa. The Gibraltar Arc, which is actually the top of a subduction zone, a short segment of subducted material, and a system of very prominent faults running right through the middle of the internal part of the Better Cordilleras. And it's in this region here that a large amount of crustal and lithospheric stretching has been taking place. Wherever you get a lot of tectonic activity affecting the upper crust, you tend to get earthquakes. So it's always worthwhile having a look at the contemporaneous distribution of earthquake activity. And here you can see there's a lot of earthquake activity associated with the overthrusting to the north and also to the south. There's actually an accretionary complex developed in the Atlantic Ocean here, which generates a certain amount of seismic activity. And this is thought by some people to be responsible for the 1755 Lisbon earthquake. Then also within the stretching part of the crust, there's quite a lot of seismic activity as well. These are not the smallest earthquakes, which would be a denser pattern, but medium-sized and larger ones. And there's quite a strong termination of the seismicity along this fault system, which is called the Trans-Aldebaran shear zone. The sea to the south of Spain is called the Aldebaran Basin. Now, of course, I imagine everybody is familiar with the ideas of plate tectonics, and particularly the idea of subduction zones, where you have, as in this upper sketch here, subduction of oceanic lithosphere beneath a continental margin. This more or less corresponds to the situation that we have in the Eastern Pacific, the Andean margin. And that's fine if you've got the velocity of plate movement across the ocean basin being equal to the velocity of subduction. What will happen then is that the bending part of the subduction zone stays where it is, it doesn't move. But you can also imagine a situation where the velocity of convergence, movement across the ocean floor, is less than the velocity of sinking. So sinking is running faster here. So what inevitably happens is that the hinge tends to work its way backwards. So it's migrating from here back to here. And this is a concept that was introduced about nearly 30 years ago, and it's called subduction rollback. And an inevitable consequence of that is that, particularly when you've got continental crust behind it, is that you get stretching of the crust, stretching of the top layer of the creme brulee, and then stretching, more ductile stretching of the upper mantle as well. So this is the thing that all of these three areas in the Western Mediterranean have in common. We're just moving a little bit eastwards to look at the Italian situation. We have a short subduction zone segment here in the Calabrian arc. We have overthrusting in the southern part of Sicily, and the Apennine belt, which is trying to push itself over the Adriatic Sea. And so this is a section of subduction zone which is rolling back, it's migrating down towards the southeast, and as a result, it's driving the opening of the Tyrrhenian Basin. Now just look at the disposition of red rocks on this map, on the exposed islands and bits of continent. We've got red rock in Sardinia there. We've got the Etna complex there. We've got the Aeolian Islands, including Stromboli, which is continuously active. And you've got Naples, Vesuvius, and Campo Flegrei, and the Alban Hills volcanics. These are all very much the same sort of age. They're uppermost Miocene through recent in age. And what you can't see is what's going on under the sea, because one of the consequences of stretching the lithosphere is you thin it, and that tends to make it subside. So there's a possibility of oceanic waters flooding it. There will. So there's volcanic activity associated with the stretching. And we can then ask ourselves, why do rocks melt at all in the upper mantle and lower crust? There are three reasons why rocks can melt. First of all, if you increase the temperature, that can cause melting. Then if you introduce water, which is the usual argument for a conventional oceanic subduction zone, introduce water into the overriding plate, that will lower the melting temperature and cause the generation of large quantities of melt. But the other way is by depressurizing rocks, because the melting temperature of mantle rocks tends to decrease as you lower the pressure. So if you have upwelling of mantle as a result of stretching, that can result in melting of the lower crust and or upper mantle. And that's probably what's going on here. You've got depressurization, melting. That's another view on a smaller part of the Calabrian arc, this time illuminated with GPS vectors, global positioning satellite, present-day displacement vectors. And you see that material is being transported towards the southeast. And there's a marked discordance in terms of velocities between what you have on the island of Sicily and what you have in the Ionian Sea. And there's a very, very well-marked fault system, which is called the Alfeo-Etna fault system, which has Etna sitting on top of it. It also has a Stromboli and the other Aeolian volcanic islands sitting on it here. And what seems to be the consensus on how to interpret this is that we have a bit of asymmetric pulling apart here, so that this fault system is developed on this side of the arc, but it hasn't really got going on this side of the arc. And if we take a view looking down towards the southwest, from up here down that way, this is what we might see. This is our subduction zone. This is the subduction of the Calabrian arc. And we have rollback, so that this hinge is migrating back that way. And as it does so, it stretches the back arc region, the crust and lithosphere in this Ionian Sea region and in Calabria. And relatively little is happening on the other side of this fault, which is formed as a geometric consequence of the differences in velocities between here and here. So this fault is able to sample that region of upper mantle melting, which is giving rise to, for example, Etna, which is perched right on top of here. Now, this kind of fault has been given the name a step fault, which means a subduction, transform, edge, propagator fault. A step fault. It's quite a mouthful, and it was, of course, invented by French geologists. The French are always in love with acronyms. They absolutely love their acronyms. So that's a term that they use to describe this particular kind of disjunctive faulting between stretching lithosphere and relatively non-stretching lithosphere. This is a view southwards from the town of Taormina on Sicily, looking southwards over the Ionian Sea, and you have Etna. It's a big chunk of rock, that volcano, a lot of basalt there. And bearing in mind that to produce that basalt, it only represents 3% volume melting of the periodicite at depth. So you can imagine just how much upper mantle has been involved in sampling these basalts to produce that enormous volcanic edifice. But the Alfeo Etna line is passing right through here, right through those trees and down towards the south. Moving a little further east again, we have the situation in the Hellenic arc, which is another rolling subduction zone, which transforms itself into a region of overthrusting, form the Hellenic mountains. And we have, with these GPS vectors, very, very strong stretching around an arcuate pattern in the Aegean Sea basin. And this simply does not propagate onto the other side of the North Anatolian fault, which is the bounding fault which is bounding, stretching lithosphere from relatively non-stretching lithosphere. The North Anatolian transform fault, continental transform fault, wants to join up with the Kefalonia transform fault, but it hadn't quite managed to bridge that gap just yet, but it's well on its way. So when we look at the GPS vectors in all three of these regions and plot the velocity represented by the GPS vectors versus distance from the rolling hinge, you see a more or less linear relationship in each case between the velocity and distance. And that's exactly what you'd expect if you've got stretching with a constant strain rate in the stretching, back arc stretching region. That will result in the velocity vectors increasing from far away from the subduction zone until you reach the top of the subduction zone. So in the Aegean, we've got velocities on top of the subduction zone present day of 30 millimeters a year, and decreasing linearly with distance away from it. In places like southern Spain, we have much slower rates of spreading, only 5 millimeters a year at the present time, but we can estimate what that would have been in the upper Miocene, and that would have been much more like this. It would have been 25 millimeters per year. So this is a very characteristic feature of a stretching block of lithosphere. So in southern Spain, going back to southern Spain, we have GPS vectors in here, which are getting longer as we go towards the subduction zone. So the wedge here is uniformly stretching. And what that means is that the relative slip quantities, slip rates along these bounding faults increases from 0 here around Alicante to a maximum where it meets the subduction zone. This wedge-shaped region bounded by two faults is in fact superimposed on a pre-existing tectonic arc, which was already undergoing some stretching. And we can illustrate that with this cartoon. This represents the pre-existing pattern of overthrusting to the north and to the south. There was stretching taking place already in this arc, but then around 12 million years ago, it decided to focus itself into a much more strongly demarcated wedge. It's like a slice of cheesecake, and it's sort of stuck here, and someone's trying to pull on the cheesecake, and as a result, managing to stretch the thing as it pulls that wedge out from the rest of the cake. So we end up with two faults with opposite senses of movement, accommodating the movement, and the amount of movement is increasing as you go from the pinning point, the zero displacement point, to the subduction zone. And you have in the upper crust lots and lots of extensional faults, low angle normal faults developed inside the wedge. Within that wedge, metamorphic basement blocks tend to be brought to the surface where they become called metamorphic core complexes, and in between those you get upper Miocene intramontane basins. This is at the right-hand edge of that wedge. This is one of these bounding faults. It's the right lateral fault. It's called the internal external zone boundary, and this is the Transalbaran shear zone, which is made of a number of fault segments which have got different names on shore. Inevitably, different people give different names to parts of the faults, but the overall shear zone, I've tended to work on this bit around here. And superimposed on top of that, you've got these circles representing the larger earthquakes, and the colored contours are the smaller earthquakes, the ones that are smaller than about local magnitude 3. And you can see how the Transalbaran fault system effectively acts as a boundary between seismically active material and much less seismically active material. So the fault system is a boundary between deforming and less deforming crusts. So it doesn't necessarily mean it's going to generate big earthquakes. Nevertheless, from time to time, it does generate earthquakes. And there's a lot of contemporary seismicity of relatively low magnitude in this region. This is one which affected this town of Bullias in 2005. And even smaller earthquakes, when they operate on unreinforced masonry, will cause a disproportionate amount of damage. A magnitude 4.4 in the UK would probably produce very little damage indeed. The odd chimney pot might fall down. So there's another sort of more complete cartoon-like overview. We've got the accretionary complex, which is offshore to the top of the subduction zone where it is now. This is where the subduction zone top was estimated to be at about 12 million years before the present. Here we've got these two bounding faults, the Transalbaran shear zone and the Corriente internal external zone boundary with their opposite senses of slip. And you have stretching in that wedge produced as a result of the rollback. There was, before this wedge became established, already an established collection of subduction-related volcanics, andesitic volcanics forming an arc in here. And one of the interesting things that you see since that was established is how the Transalbaran fault zone, the Carboniferous fault in particular, slices right across the nose of this volcanic arc. So this section of fault onshore separates non-volcanic material from volcanic material. And in fact, the volcanics were active because what we see are dikes shooting up the fault zone, and they would have fed eruptive centers all the way along that fault zone when it was strongly active. So this diagram is to illustrate the concept then of a stretching fault. You're familiar with the idea of faults existing between relatively rigid blocks of rock, undeformable blocks of rock, and all the deformation is concentrated in the fault zone. But here we've got a deformable block on one side of the fault zone, which is stretching those circles into ellipses. The ellipses are deformed by the same amount everywhere, but the amount of slip on the fault increases as you move along here. And you have a relatively rigid block on the other side, which is not really deforming at all. So that's the concept of a stretching fault. Now, the idea of faulting as a velocity discontinuity, which is what we're talking about here, is not a new idea. It was proposed over 60 years ago as a purely mathematical construct by Helmer O'Day. And now, of course, we can see it applying to geology in the field. It's been quite common in the earth sciences over many decades to find that mathematicians somewhere have managed to come up with a description of something which seems completely irrelevant to anything, and then a decade or two or six later, we suddenly find that this is something which describes things that we see in the earth. If you haven't come across it, I want to introduce you to the concept of seismic shear wave splitting. When you stretch upper mantle rocks in particular, you pull the olivine crystals into a kind of an alignment. They have a preferred orientation, and this makes them mechanically anisotropic. So if this represents the surface of the earth, and we've got these stretched crystals which are being elongated that way, when we have seismic waves coming vertically from beneath, such as we have in the case of teleseismic shear waves, by teleseismic it means that they're coming from earthquakes which were produced on the other side of the planet. So by the time they arrive here, they're coming up vertically. These shear waves are passing through deformed upper mantle, and as they pass through, they get split into two waves vibrating at right angles to each other. And the one which is developed parallel to the stretching direction is the fast wave, so that arrives first, and the one which is vibrating in the opposite direction is the slower one, so that arrives a little bit later. So we can measure the time differences of arrival of split shear waves and hence measure the anisotropy of deformed rocks in the upper mantle. When we look at the south of Spain, we find this is something which works rather well, because these little bars here represent measurements of shear wave splitting fast orientations. These are the fast polarization directions, and they are telling us with their preferred orientation that these rocks have been stretched in a northeast southwest direction. And you couple that with the existence of these extensional faults, these normal faults, which are accommodating the boundaries together with some linking wrench faults of Miocene sedimentary basins, and you have a compelling picture of lithospheric stretching developing. So I mentioned before that the Transalpine shear zone, and particularly the Carbonarious fault, this particular part, is cutting through the volcanic arc. So we see that volcanic activity on geological grounds, cross-cutting relationships, accompanies the movement on the fault. And we can use those volcanics, and we have used those volcanics to date fault movements quite precisely. And we find that the movement on this fault zone is very strongly focused between 12 million years and 6 million years. after which it reduces very considerably, so that now we see the same pattern of movements taking place at the present day, but with a much lower degree of intensity. So let's just take a closer look at some of the geological features of this particular corner, the bottom right-hand corner of Spain. It's about 50 kilometers or so, from a bit more than that, from one side of this picture to the other. And we're looking more or less towards the west. So this is the coast, obviously. There we have the Carboniferous fault zone. It forms a very well-marked linear feature on the ground. We have the volcanic terrain of subduction-related andesitic volcanics to the south. These have been largely removed to the north by movements on the fault. The estimated amount of movement on the fault at this particular locality is about 40 kilometers. And this increases to about 120 kilometers by the time you've crossed the Almeria basement and arrived in North Africa. Towards the north, we have these uplifted blocks of basement, the Sierra Almeria, the Sierra Cabrera, Sierra Los Filabres. These are the dark areas. These are basement metamorphic rocks, and these are separated by sedimentary basins, intramontane basins, which collect the erosional debris from these uplifted blocks. So we'll have a look, first of all, at some of the features of the Carboniferous fault zone, and then have a look at what's going on in the Sorbas Basin, because that's a good place to investigate contemporaneous features associated with basin formation forming at the same time as this fault zone is active. This tract of exposure, I first drove alongside it in 1978. And I came very close to having a serious accident by driving off the edge of the road and ending up in the bottom of the valley. I was just so gobsmacked when I saw that exposure, because this is an exposure of the Carboniferous fault zone. The whole zone here is about 50 meters wide, but the main movements are focused into this 5 meter wide tract, which is running through here. And movements on this fault are uplifting metamorphic basement rocks to the north, and they are relatively downfaulting volcanic rocks to the south. So we've got this section of the picture is focused into this part of the cross section. That's what you're looking at. So we've got uplifted basement rocks to the north, and we've got these volcanic rocks to the south. There are older volcanics which are deformed, folded, and there are younger volcanics which are fault displaced, but they're not internally distorted. So I mean, this is the reason why this is a very compelling place to work. Now, this is what these volcanic rocks to the south of the Carboniferous fault typically look like. I mentioned there are two sequences. There's a younger sequence, which are the red ones here. This is the contact. There's an unconformable contact with underlying greener looking volcanics. And these are dominantly andesitic in composition, the sort of thing you would expect to find in association with subduction. Within the fault zone itself, there are lots and lots of indicators of the sense of movement. For example, in this particular case, you've got a faulted contact between dolomite and ground up metamorphic schists, and this is developing mechanical wear grooves, which testify to the dominantly strike-slip horizontal lines of movement on this fault system. A bit further north, this is an exposure of the Andalucia fault, which is another part of the same fault zone. Lorca is a place where in 2011 there was a damaging and fatal earthquake, which was associated with movements on this fault zone. This is crushed up material, crushed up schist, which is in contact with relatively undamaged schist, and off the picture there are sedimentary basin rocks. So they're the sort of things that you see in association with the Carbonara fault zone. If we now turn our attention to the Sorbas Basin, in particular to this particular bit, we can see some of the things that were forming there at the same time as that fault zone was active, between 12 and 6 million years. So the next picture is a geological map of that area. And the key features on this map are, first of all, the purple and brown rocks. These are metamorphic basement rocks forming a tract passing through here, which have been uplifted as a result of the extensional faulting. There's another chunk of basement rocks over on the other side in brown here as well. And in between, you have effectively a down-faulted block of upper Miocene sediments, and it's in two parts. Well, first of all, I should mention this is the bounding fault, the Carbonara fault zone, with the volcanics to the south. So movements on this fault, I hope to demonstrate to you, are linked to what happens in this area. The blue stuff is the Mycenian, are the Mycenian deposits in this area. These are the post main stretching deposits. These are relatively horizontal rocks deposited between 7 and 5 million years ago. They're very interesting in their own right, but for reasons that I won't go into at the present time. And these things sit with unconformity. You can see the unconformity there on top of this sliver of older, slightly older Mycenian rocks, not slightly older Miocene rocks, and these are Teutonian in age. That's the stage which lies underneath the Mycenian. And there's not much of it to be seen there, as you can see. It's rather limited in exposure, and quite a lot of the action is buried underneath these irritating Mycenian rocks. This is a general view over that area from metamorphic basement rocks that we're standing on here, across the Teutonian lower part of the basin fill, and capping the tops of these hills as the base of the Mycenian sequence, with the Mycenian more or less horizontal sediments sitting on top. That's the Mycenian unconformity. It's an unconformity of regional importance throughout the Western Mediterranean. Marks a big change pretty much everywhere. We move a little bit closer. Oh, before we go a bit closer, this is what metamorphic basement rocks look like. They are basically metamorphosed organic mudstones. They are graphitic mica schists now, and this is what we typically find in this region in the metamorphic basement. And that's the Mycenian unconformity. It's a very clear contact. And underneath that, there are Teutonian beds, which are dipping very steeply, locally vertical and even overturned. Now, it might not be very obvious that the rocks are dipping that way, but you just have to take my word for it. They really are dipping at about 70 degrees towards the left. So it's a really major unconformity. So this next picture is a kind of an oblique view onto that area, but with the Mycenian rocks stripped off. So we can imagine then what the underlying rocks look like if the Mycenian rocks hadn't been deposited. This is the fill of the Teutonian Sorbas Basin, and we've got uplifted basement rocks to the north, and we've got uplifted and fault-bounded basement rocks to the south. And this contact that you see in here between the basin fill and the basement is a fault contact. It's a low angle extensional fault contact, and it detaches these sediments from the basement. So these rocks are sliding down into the deeper part of the basin, but it's not just a rigid block sliding, as you'll see in a moment, and it's in response to that east-west stretching that I've been harping on about all the time. The next pictures are of this particular area where you can see exposed these low angle extensional faults. So this is a very typical appearance of a low angle extensional fault, so-called detachment fault. You've got basement rocks beneath, and they've got wear grooves, mechanical striations on them. And on top, you have red conglomerates of the Teutonian sequence. Here's another place a bit further along strike where the faults are dipping a bit more steeply. They've been slightly tilted, and you have a little outlier there of Teutonian sediment sitting on top of basement rocks. Now, these detachment faults formed more or less contemporaneously with the uplifted basement blocks. And we can tell that because we sometimes find that these faults get rotated through 90 degrees until they end up vertical. So this is what was a gently dipping, not very far horizontal, detachment fault on the boundary of the basement, which has now been rotated up to vertical. Unfortunately, you can't see on the picture, but there are slickened lines on this block, which indicate the line of movement. So it looks like a strike step fault, but it's not. It's a rotated detachment fault. And this next picture is another one of my block diagrams, hoping to clarify the geometry of what's going on. This yellow area in here is basin fill, Teutonian basin fill of the Sorbas Basin. Here is the uplifted basement block, and this is the detachment surface, which is allowing all this stuff to slide down into the basin. There are differential uplifts to be seen between different parts of the basement. So the Sierra Cabrera basement here is uplifted more than the basement on this side. But on this bit over here, this bit of basement is lifted up higher. So it's a kind of a scissors fault. So the sense of movement actually changes from one end of this fault to the other end of the fault because of these differential uplifts. And it's these differential uplifts which are intimately related to the way in which the sedimentary cover is shed into deeper parts of the basins. So this is a part of the exposed Teutonian sequence with the basement rocks lying to the south, and the yellow stuff is that Mycenaean material which is unconformably overlying with marked unconformities, you can see here. And these rocks are quite strongly deformed, and they were deposited in a very, very tectonically active environment because they are basically a sequence of quite dramatic gravity flows, turbidity current flows, with very, very spectacular developments of graded bedding. And sometimes some of these beds entrain within them blocks of metamorphic rocks, which are the size of a car. All of this stuff being shed down off the basement material to the north. All of this part of the sequence is developed between 13 and 7 million years, which is the time when the peak of volcanic activity in the region was being felt. So on the one hand, we can see detachment and sliding of the cover rocks, sedimentary rocks off the rising basement, but we can also see evidence for actual stretching of the cover rocks within the rock mass. So here is part of a section which is shown interpreted here, and a bit of a close-up of part of it. This bit is over here somewhere. And there are lots and lots of extensional faults developed in here. And you can see from the geometric form of these wedges of sediment and the way the cross-cutting relationships work, that this sequence was actively being stretched more or less at the same time as it was being deposited. So we have stretching within the basin fill as well as sliding of the whole rock mass down that rather gentle slope. So these irritating Mycenaean rocks that I mentioned before are obscuring quite a lot of the Teutonian basin fill. And what we really do need to know in order to reconstruct the history and the geometry is just what is the shape of the bottom of the basin? How deep does it get? How does the thickness of the basin vary over the outcrop area? And one way of doing that is by gravity, a gravity survey. We wanted to know the depth to the basin floor in order to describe the overall basin geology. So we carried out a regional gravity survey, which allows us to see through that cover of Mycenaean rocks, and we can detect from the gravity variations the interface between the relatively less dense sediments, because they're very porous, and the relatively more dense underlying metamorphic basement rocks. And this is a contour map of the shape of the bottom of the basin. And you can see that it forms a valley. The bit that we were just looking at was just this bit in here. So you can see what a huge proportion of the basin, the Teutonian fill of the basin, is covered by Mycenaean deposits. So armed with an estimate of the depth of the bottom of the basin, we can start to make a series of cross sections. And these are some north-south cross sections, different distances along the basin. This is the furthest westward. So you can see this informal looking part of the wedge of Teutonian basin fill. It's bounded to the south by uplifting of the Sierra Almeria, which has basically flipped these rocks up to the vertical. And you can also see the Mycenaean unconformity here, relatively undeformed, which is obviously burying a substantial part of what would be the outcrop of Teutonian deposits. Further north, those sediments thin down, so you can see the Mycenaean cover, and further east still you have no sediments exposed at all. You've just got the metamorphic basement rocks exposed, and the whole thing has behaved rather like a rigid block which has popped up. These little arrows represent the more or less rigid upward displacement of these basement blocks, which are controlling the shape of the basins and controlling how they evolve. So if we draw another cross section, this time from east to west, we can see what's actually going on here. First of all, the basin, so the cross section is bounded at the top by this line, which is the unconformity between the Mycenaean cover and the underlying Teutonian rocks. And there's about 2.5 kilometers of Teutonian rocks at the western end, thinning down to nothing. And there's a detachment fault, two detachment faults. There's this one in the basement, and then there's the one which you saw pictures of running along the bottom of the sediments and merging with these other faults at depth. So that as this brown basement pops up, pushing up more here than it does over here, that causes this whole slab of sediments to slide off. And I'm talking interpretation here, but of course what we see in terms of the shapes of these rocks, that's fact. So we're interpreting this to be sliding off of this material, and as it slides, it starts to kink, it starts to fold, and gets thrown into this enormous monoclinal kink. Remember that marked unconformity that we saw with about 70 degrees angle between the Teutonian rocks and the overlying Mycenaean rocks? That's somewhere about there. So although we can only see a certain portion of the Teutonian fill now, we can deduce the shape of the deformed Teutonian fill as it would have been before the Mycenaean was deposited. Quite a lot of rock's been eroded off here, but this is inferred to be a gravitational collapse structure, a very dramatic feature to develop in a space of just about 5 million years. Now, one of the things that concerned me as a petrophysicist was how did these rocks manage to deform? What were their mechanical properties that could allow them to be thrown into this large set of fold structures? We did carry out an investigation of the petrophysical properties, mechanical properties of these rocks to see how well they fitted in with the story. But that's another story which I won't go into right now. So to conclude then, what we've got is a basin here which shows a two-stage evolution. First of all, between the Serravalle and the top of the Teutonian, we have deposition on an east-west extending crust of metamorphic basement. And we're talking quite rapid extension, rather like we have at the present day in the Hellenic arc. This region was bounded to the south against the Carbonara stretch and transform fault, which was part of the Transalbarine shear zone. And this is demonstrably, or was demonstrably active. Both of these things were forming at the same time. The extension of the basin fill and the faulting and the volcanic activity. This very intense activity seems to have subsided in the late Teutonian. Then we have this uplifted erosion, the deposition of the unconformably overlying Miocene rocks, and eventually plioquaternary systems in an emerging continental environment. But the most rapid extension of all was during the period 12 to 7 million years, but we can still recognize at the present day, GPS vectors, the same kind of movement geometry, but much subdued compared with what it was during the Teutonian period. A very violent time. So I'm going to stop there, and I want to thank you very much for listening, and invite any questions that you might want to ask. Thank you very much.
Well, thank you very much, Ernie. That was a fascinating talk, and a lot of tectonic activity in a relatively short time. So I'd like to open up the floor to anybody who has any questions after the talk there. You can use the raise hand on the reactions button if you want to, or put up your video and unmute yourself and ask directly. Silence.
There's a few names I recognize in this list of people.
Yeah. Does no one have any questions?
You see, Rich, I told you I put them to sleep.
Yeah, nobody's put the video on either, have they? So, you know, we don't know if they're even there.
So put the sound on, we'll probably hear the snoring.
Yeah. Hey. Well, I thought it was interesting when you were trying to determine the basin, the Sorbus basin, given you've got that thick cover. Are there any boreholes that you can use to
Well, there are boreholes.
Figures?
There are boreholes, but they're not actually very useful. The main reason that people drill boreholes in that region is for water for irrigation. And the really peculiar thing is that they tend to drill boreholes for about 150 meters depth, which keeps them in the Mycenaean. And the Mycenaean is made of not very porous materials. So although they form aquifers, the volume is rather limited. But if they were to push those boreholes right through to those 2.5 kilometers of Teutonian coarse-grained porous sandstones, they'd find that it's going to be an artesian basin. Nobody seems to have taken that up yet, but there should not be a water supply problem in that basin.
Because as a region, I think it does suffer from water supply.
Well, it is a semi-arid region. It suffers from processes of desertification. But I think part of the problem is that people don't think on a big enough scale in terms of using the geology to infer which is the best place to look for water.
Yeah, yeah. Yeah, because that is shallow, 150 meters.
So there aren't, as far as I know, there aren't any deep boreholes. What they do have in the eastern part of the area is a high-speed train line, which has been built in a series of tunnels from Almeria, and it will eventually arrive in Madrid. And so it goes through that region, and that does involve still quite shallow boreholes, but in the Tectonic rocks. But like so many of these projects, it's been put on hold because they've run out of money.
Yeah.
And the other problem is that the small towns along the route, everybody wants to have a station. So they all say, well, you can only go through our local area if we can have a station, which is the last thing you want to have on a high-speed train.
Yeah. So in this region, there's the Mycenaean and evaporitic facies.
Yes.
Yeah.
As I said, the Mycenaean is another story. And if you look in the literature and try to estimate the number of papers that have been written on the Tectonic versus on the Mycenaean, you'll find that 95% of them have been written about the Mycenaean. And that's because of the evaporites. And because the Mycenaean represents the period of time when the Mediterranean dried out completely, the Mycenaean desiccation, the Mycenaean salinity crisis, and within the Sorbas Basin, you have the thickest sequence of gypsum evaporites anywhere in Europe. And they are quite extensively quarried to make plaster. And if you look now at your wall, the chances are you are looking at plaster from the Sorbas Basin, because that was largely worked by the British Gypsum Corporation, and it ends up everywhere in Europe.
Yeah.
There's a lot of gypsum there.
Yeah.
It's quite interesting to work out how long it takes to dry out the Mediterranean, because of course, in Mycenaean, the Straits of Gibraltar were closed off, so there was only the rivers draining into the basin. So you might like to calculate for homework how long it would take to dry out the Mediterranean, given that it's on average 2 and a bit kilometers deep. The answer is 1,000 years.
Can I just ask something, Richard?
Sure.
The Carboniferous fault zone you were talking about, I may have missed it, but I know when you were talking about when it happened, but what sort of length of time was it active over?
The main period of activity, basically from its formation, was from about 13 million years to the present. But by the time you get to the lower Mycenaean, it's slowed down a lot. So the present day rates of movement are very, very slow, measured on the order of a centimeter or two per year.
Right.
If that. Basically, you don't see much in the way of offset of Mycenaean and younger deposits, but you have huge offsets of Tectonic and, of course, basement rocks before that.
Right.
Anybody else have any questions following the lecture?
He's shut the video and muted us.
Who has? I've not done anything. Honestly. I'm just going to have a look in the chat. I haven't got any questions in the chat. Because that's another way you can ask. If you don't want to ask personally, you can put it into the chat and I can read it out. But
No. Too complex.
No?
No.
Well,
I think everything was just
Oh.
so clear that everybody understood everything perfectly.
I have one question that's just come into the chat. It's from Martin Hayward. Why did the rapid extension develop?
as I mentioned, the extending wedge in southern Spain, the developing wedge in the Calabrian arc, these seem to be localizations of an already extending region, but spread over a wider area. In southern Spain, there was a regional extensional post-orogenic collapse. The whole mountain chain basically fell apart. It got too hot to support its own weight. And it extended from the Bertigalian, more or less 20 million years ago onwards. And then it became localized into this narrower wedge. So maybe that's when the subduction rollback really began. What turns it from a more or less widely extending region into a narrower extending wedge, I don't know. Possibly something to do with the tearing of the downgoing slab.
Well, if there are no more questions from anyone in the audience, could I call on John Wood to give a vote of thanks?
Yeah.
John, over to you. So I'm just reading the chat. That's just someone saying thank you very much. Yeah. So yes, I hand it to you, John.
Yeah, thank you very much indeed. Thank you, Ernie. It was a really interesting talk. Love visiting southern Spain, looking forward to going there again. So it was interesting to hear something about the geology. I have to confess, I hadn't really read anything about the geology on trips when I've been there. And as an amateur geologist, there were lots of things I learned tonight that I knew nothing about. I had no idea that these things were occurring so recently. I sort of assumed all the deformation stuff you see was to do with the Alpine mountain. I hadn't realised that these things are actually only half that age, if that, which really surprised me and was very interesting. I also confess to never having heard of subduction rollback before. I'd just seen the idea of subduction going on and the Andes being shoved up or whatever. And this idea of it actually retreating back, I found really interesting and leading to that stretch. That was very interesting. I love your Bruce. Definitely, I will remember well when I see him. But it was an excellent knowledge. But I think, as a mathematician, I'll take away with me marvelous praise for theoretical mathematics, leading to them be confirmed in the real world. We're used to that with things like black holes, which were predicted theoretically, but it's nice to hear that the same thing happens in geology. So thank you very much for saying we mathematicians doing good work. That was nice. So an excellent talk. Thank you very much indeed. Really, and by the reactions or whatever, I think probably. So, thank you.
My pleasure.
Yeah, thank you very much, Ernie. Thank you. Well, Audrey, you have some announcements or some reminders for society members while you're here?